general relativity. One of the important predictions of GR is that light will be bent by massive objects, an effect known as gravitational lensing. In fact, it was lensing that made Einstein famous worldwide in 1990. And today, it's our honor that one of the world's experts in gravitational lensing, Professor Tommaso Treu from UCLA, is the closing speaker. Professor Treu received his PhD from Scuola Normale Superiore in Pisa, Italy in 2001. And then he was a postdoc at Caltech, and then a Hubble Fellow at UCLA, before becoming a faculty member at UC Santa Barbara in 2005. He moved to UCLA last year. Professor Treu studies the formation and evolution of galaxies and supermassive black holes within them, using ground-based and space-based observations, ranging from the nearby galaxy clusters to the era of cosmic reionization. He also studies the nature of dark matter using lensing observations of galaxies and galaxy clusters. And finally, he also studies the nature of dark energy through time delay lenses. So today, what happened? So today, Professor Treu will share with us his views on the nature of dark matter and dark energy through years of work. Let's welcome him.
Hello, can you hear me?
Yes.
Okay, great. So he said this mic is soft, so I have to be lively. So this question, what is the universe made of? Is a question that has obsessed me since I was a little child, but it's not really a question that has obsessed only me. I think this is a question that humans have been trying to answer since the beginning of time. And in fact, I always tell my students that one of the defining criteria of humans is that we ask useless questions, but they are extremely interesting, and perhaps they are the questions that allow us to create new knowledge. So one of the most remarkable discoveries of physics in the last 20 or 30 years is that most of the universe is not made of the stuff you normally see in a lab. So all the stuff that has been seen, say, at LHC or other accelerators, only makes up a small fraction of the mass of the universe. Most of the mass and energy content of the universe is only seen through its gravitational effects. And so it's very reasonable to try to study this stuff through gravitational lensing, because gravitational lensing only depends on the gravitational properties of the systems. So by making very, very precise measurements of the deflection of light by dark matter and dark energy in the universe, we can try to learn about their physical properties without relying on assumptions on their interactions or other properties. So I will give you a brief overview of this work. And the first thing I want to do, since this is a joint colloquium, I want to put this in the context of physics. How does this connect from what physicists do in the lab? And this is what I call the view from the Earth and the view from the point of view of the universe. So from the point of view of the Earth, we have a certain view. We think there's this tremendous achievement of the standard model of particle physics, and that's beautiful. But when you take a less, say, provincial view, and you fly away from Earth and look from the point of view of the universe, you discover very interesting things. And I will tell you some ways in which I and many other people, including Sherry Suyu here, have been trying to study this thing using the gravitational lensing effect. And since you imagine I will not tell you the answer, I will not tell you what dark matter is and what dark energy is, I will conclude with a roadmap for the future, how we're going to get to answer this question. So, if you're a particle physicist and you slam particles together to create other particles, you observe that all the phenomena you create are pretty well described by this standard model of particle physics. This is a fantastic achievement of humans, and the fact that we can describe very complex interactions and phenomena with a relatively simple model is really a triumph of physics, I would say. But probably when you go and look from the point of view of the universe, like in this picture here, this is the Hubble ultraviolet field, one of the deepest images ever taken by humans. You see that you have to deal with a very different experimental setup. So you cannot control your lab. You cannot smash galaxies together. You cannot measure these particles. The only thing you can do is select very carefully the things you want to look through with your telescope. And of course, if you were able to have dark matter goggles that would allow you to see dark matter, what you would see is something more like this. So a filament of dark matter filling space. And if you had even more sensitive glasses that would allow you to see dark energy, you would realize probably that this is the energy matter content of the universe. Most of the energy in the universe is in the form of dark energy. This is the thing that makes the universe accelerate. A quarter is in something we call cold dark matter, non-relativistic particles that are not part of the standard models. And only 4% or so is what we call the standard model of particle physics. But of course, to get to this, we have to rely on images like this one. And today, I will tell you how we use images like this one to get to learn about this. And of course, one of the greatest success stories has been how accurately we've been able to measure these things. When I was a student, we didn't even know that there was dark energy. I mean, it was suspected, but it wasn't even clear. Now you can see people are debating about the second or third significant digit of these measurements. This is from between Planck and WMAP. But to me, this is fantastic, but not completely satisfactory. Because what we really would like to know is what is causing acceleration? What is the thing that is causing this acceleration? And a simple answer could be dark energy. And this is what comes up if you Google image dark energy. This is what you find on Google. But this is just a name. And the current explanation, if you want to call it an explanation, is that it's something described by an equation of state connecting pressure and density by a constant. And this constant could be -1 if it's like a gravitational cosmological constant, or maybe something else if it's not -1. Obviously, this is a phenomenological description. It's not a profound description of what this is. But since we have no idea of what this could be, we have no fundamental theory of what this could be, this is the description we're using to this day. It's a phenomenological description of the relationship between pressure and density. Yes. And there's also another, we have other hints about what the universe could be made of. For example, inflation and Big Bang predicts the universe is close to flat. So if you take a big triangle in the universe, the sum of the angles will be about pi. So we have these sort of ideas. They're not very precise. So let's try to figure out a little more about them. So the first thing is we can use gravitational lensing to do cosmography. That is to measure these cosmological parameters. So how does it work? So Yenting referred to, of course, the famous event. This is the 1919 solar eclipse when you're observing from Earth the position of two distant stars, and one of them gets closer to the sun, and so the light from the stars is deflected by the curved space-time around the sun. In extragalactic astronomy, outside of the solar system, we can also observe this phenomenon, and usually something like this, there's an observer, us, a distant object, could be, for example, a quasar, or something else. And then in between the two of us, there's a massive object, like a cluster of galaxies, or a galaxy, or maybe a star, or something else. And if the gravitational field of this is sufficiently strong, and if the alignment is sufficiently good, you can create multiple images. Now, these multiple images are remarkable because they allow you to measure things about the mass distribution, even though you don't need to see anything. So this thing could be completely dark, so non-interacting with light, and we would still be able to measure its mass by looking at the deflection angles. So the deflection angle is a measurement of mass independent of the nature of what is doing the deflection. And there's more to it. So if the source is variable in time, and the observer is here, the light path of the two images has a different length. So this image has to cover a longer distance than this one, and so this image will arrive at a different time. In general relativity, things are a bit more complicated because there's another effect called the Shapiro delay, whereby the arrival time is also modified by the gravitational potential of the curvature of space-time. And therefore, the arrival time of the images is not the same. So if the source is variable in time, so for example, if you're seeing my talk behind a massive cluster of galaxies, you may see two instances of my talk separated by a few years, or you can go on YouTube and do the same thing. But okay. So this can be understood in terms of normal optics. It's called the Fermat's principle. So like in normal optics, images form at the extrema of the arrival time surface. The same thing is true in gravitational optics. This is the arrival time surface. And as you can see, it's interesting because it's proportional to a distance. This combination of distances is known as the time delay distance. And the two effects I was describing before, the geometric time delay and the Shapiro delay. And the things you can observe in gravitational lensing are the image fluxes, positions, and arrival times. So from this information, you have to try to infer something about distance. Because remember, like for example, I'm sure you all know about the Supernova 1A experiment. The Supernova 1A experiment measured the acceleration of the universe by measure how distances depend on redshift. Here we can do the same thing, but we're measuring distances using cosmic clocks as opposed to standard candles. So how does it work? You measure the difference in arrival time between two images. This will depend on will be proportional to the time delay distance, which is a function, is inversely proportional to the Hubble constant. This is the present day expansion rate of the universe. And then a weakly varying function of the omega matter content and W, okay? So, and other cosmological parameters. So the steps are the following. You first measure the time delay between two images. So you stare at something for a long time, you measure the difference in arrival time. Then you measure and model the gravitational potential, that is this thing here, the gravitational potential. You infer the time delay distance, and then once you have a measurement of distance, you infer cosmological parameters. These are the steps. And these are important. So people may tell you that cosmology is solved by CMB, but it's not actually true. So this is a plot taken from the Planck 16 paper. There are recent versions of it. If you take the CMB measurements in red, shown in red here, there's a strong degeneracy, for example, between curvature and the Hubble constant, or between, say, sigma 8 and curvature, many other, like the mass of neutrinos, W, and so on. So it's true that for a 6-parameter lambda CDM model, the CMB measures very accurately everything, including the Hubble constant. But if you start relaxing some of the assumptions, since most of the information from the CMB comes from very high redshift, you don't have much leverage on what's happening at lower redshift when dark energy becomes important. So it's very important to combine a lower redshift probe, something that happens at redshift below 2, with the CMB in order to learn about the varying nature of dark energy. And this is shown here in these blue contours. These blue contours are the combination of the CMB data, cosmic microwave background, with the baryonic acoustic oscillation. So baryonic acoustic oscillation is a signal at lower redshift. When you combine that with the cosmic microwave background, all the limits on neutrino masses, curvature, and so on shrink to a much smaller. Still degenerate, of course. And these are only models with one additional parameter. So if you were to add many more additional parameters, you would have many more degeneracies. So you need independent probes to break all these degeneracies. And this is shown in this beautiful paper by Sherry last year, where it was shown that with a single lens, you can go from big degeneracies in the CMB data, like for example between curvature and Hubble constant, to much more constraining parameters. And see, lenses seem to like to want the universe to be flat. Now, depending on your inclination, if you're inclined to believe theoretical prejudice, this is good. If you're agnostic about theoretical prejudice, this is an interesting coincidence that the universe likes to be flat. So, of course, this is not a new method. This has been around for more than 50 years now. It was actually proposed in 1964 by a Norwegian astronomer long before gravitational lensing on cosmic scale was discovered. And then when in the 70s people discovered lenses, they got all very excited. They can say, okay, we can do this, use this to measure cosmology. So in the 80s, they spent a lot of time trying to measure time delays. And initially, it was very difficult, and then eventually they succeeded. In the 90s, when they had the time delays, they started to combine this with mass models to derive the Hubble constant. But it turns out that they were getting very strange numbers, and especially very small uncertainties. And in hindsight, now we know that they were considering models that were too simple, and they were not constrained enough by the data, and that was the reason why they were underestimating the uncertainties. So over the past 15 years, really, a group of people have developed many tools that include like modern monitoring, where you measure these time delays with a lot of accuracy. You use null-lensing information like the motion of stars. You use information from the sources of the variable sources. And finally, in 2010, this was all put together in a beautiful paper by Sherry, when you get down to 6-7% precision for a single lens. Now, this should be contrasted with, for example, Supernova 1A. A Supernova 1A gives you a comparable precision, but on relative distances, while this gives you absolute distances. Okay, so it's an intrinsically different measurement because you have an absolute distance, not just a relative distance. And of course, the nice thing of all this is that in 2014, on the 50th anniversary of the initial proposal of the method, we discovered the first multiply image supernova. So it was named Refsdal. And in case you haven't seen it, I want to show it to you. This is a beautiful example. So there's a cluster of galaxies called MAX 1149, and this cluster is lensing a background galaxy, here shown in blue. And this background galaxy is imaged at least 4 times, if not 5. And one of the spiral arms of this galaxy is further imaged 4 times by this galaxy in the cluster. So there's a lens in a lens. You kind of have a system, a hierarchical system of lenses. And the nice thing is that this was an image taken before February 2014 of this region here. And in November 2014, we saw 4 images pop up like this. Okay, so this is the difference between these 2 images. And so a supernova exploded in the spiral arm of this galaxy, and we saw all 4 images at once because the difference in arrival time for this system are small compared to the duration of the light curve. It turns out actually the light curve of this supernova lasted for more than 6 months. It peaked in April 2015. And so we kind of saw like, if this supernova were a person, we had a picture of the person when they were like 30, 35, and 40. And we were really at the same time. And then as time goes by, we were able to see their entire life. One interesting thing is that, of course, there are other images. So we may wonder, will the supernova appear in the other images as well? And the prediction is yes. We think this was immediately recognized. We think that another image will appear here. And we think an image appeared here about 10 years ago. And unfortunately, that's gone. We cannot see that. But we can certainly hope to see this one in the near future. So there's an approved program with Hubble that will point at this cluster on October 30th. And so we will see if the supernovas come back or not. So like this is kind of like astrological forecast for a star will appear over there in your life. So stay tuned and we'll see what happens. Okay, the problem with this cluster is that it's too complicated. Okay, so the mass distribution here is too complicated to do cosmology here. So what we have been really focusing on for this cosmology experiment has been this galaxy scale lenses, where the deflection is done by a single galaxy, pretty much like this object, but it's in isolation. And so you have to solve 4 problems to get there. The first one, you have to measure time delays, and those can be measured to 2 or 3% uncertainty. Then you have to measure astrometry, that is the position of the images. That can be done with millisecond precision using these techniques. Then you have to be able to model the lensing potential, and this has been demonstrated now to be possible with this level of precision. And the fourth thing that was a little harder to recognize, that a lens doesn't live in isolation, it lives in a complicated universe. And so if you want to get very precise, you need to model the entire distribution along the other side. Anyway, all these things have been solved now, fortunately, we think. And so let me just illustrate the progress on each of these 4 things. This is the progress in light curve measurements. This is one from the 80s. This is one from a few years back, and you can see that the variability of this shows flux as a function of time. The amplitude of the variability of the flux is much larger than uncertainty. So you can clearly see by eye here that this image D lags image A, B, and C by about 100 days. You can measure it almost by eye. So you can measure it with a precision of a few 2-3% with proper techniques. Okay, this is shown over 10 years or something.
What's the gap?
What's what?
No data, the gaps.
Yes, because there's the objects become invisible, go behind the sun. They're too close to the sun, so they will be visible during the day, but it's hard to observe them. So you have seasonal gaps. So this is a configuration when you have 3 images near to each other, so they have very short delay and a longer delay here. Okay, so and this is an improvement in the way we measure the lens potential. This is what Schechter and company had to work with in 1997. And this is the quality of the data that Sherry had in 2012, where she wanted to model the system. This is the data, and this is the model. So you can see that there's thousands of pixels here, and every pixel contains information. You can use that information to constrain the gravitational potential to the level of precision that you need. And then the third point.
Just curiosity, what's the dot actually next to the center?
This?
Yeah.
It's a satellite galaxy. It's kind of like the Magellanic Cloud for us. You know, little satellite galaxies.
So these two could merge.
Yes, probably. But in a few billion years. So we don't have to worry about that today. And so the other thing is that we need other stuff like the motion of the stars. So the motion of the stars is a way to measure the gravitational potential pretty much in the same way as we use the motion of the planets around the sun to measure the mass of the sun. We can use the motion of the stars in a galaxy to measure the mass of the galaxy. This helps. And then finally, the structure along the line of sight, it was ignored for a few decades until it was finally recognized that you can make a difference at the level of up to 10%, even if you're not correcting properly. So you put all this stuff together, and we've done this for one lens called B1608, and this is the result for this one lens. And you can see at that time, the constraint from a single lens, B1608 plus cosmic microwave background, were comparable in size to baryonic acoustic oscillation and supernova at that time. But interestingly, they were significantly almost orthogonal to the constraints from the baryonic acoustic oscillation. So if you have both the information from lensing or BAO and supernova, we can tell that the universe wants to be, W-1 and flat. So the combination of these diagnostics selects a universe where the dark energy is like a cosmological constant and the universe is flat. So, of course, nobody believes the method until you've shown that the method can really measure something new. So if you already know the answer, it's very hard to convince people that you're doing something right and you're not actually finding the answer you're looking for. So what we embarked on doing was a blind analysis of the system. Now, how does a blind analysis work? It works in this way, that you measure things, but you inside your code that makes the measurement, you have some lines that remove the average of the posterior distribution function of the parameter. So you never see what the value of the parameter is. You only see 0 for all your parameters, so that you cannot tweak your data, say, oh, let me try to change this or change that until I get the right answer. So you do this blindly, and only at the very end you decide to unblind your results. Now, a very tricky part of this is that in order for this to work, you have to really be serious and commit to publishing whatever you found. And I remember, when Sherry was doing this and we were in Santa Barbara together, obviously she was very stressed because, what if you find that, what if we find that the Hubble constant is minus 32? That's going to be very embarrassing, and she was correctly worried because her name was going to be the first of the paper, so she was going to be famous for having found the Hubble constant to be minus 32. So we had an internal agreement of the team that if the Hubble constant was negative, we will not publish the response. But so contracting universe was not acceptable, but everything expanding was acceptable. Okay, so that was the agreement. And I remember this very intense final teleconference with all the co-authors where Sherry had written an interesting piece of code that would reveal the answer to all the co-authors simultaneously. So she didn't know the answer. Nobody knew the answer. And when we got to the end of the conference, everybody was happy with the analysis. She said, okay, this is the answer. So there was a moment of, say, anxiety. And this was all the inputs. And I will not tell you the answer until I tell you what happened. So this was the observed image. And she had to model the light distribution of the extended source, the mass distribution of the lens and the satellite, the light of the lensed quasars, these are accretion disks around quasars, the light of the lens, and the time delays. You model all this stuff and you end up with a model that looks like the data. Very nice. Then this was a spectrum taken from the Keck Observatory showing you the motion of the stars in this galaxy. This is a characterization of the line of sight obtained from millennium simulations and other methods. So you combine all of this together and you end up with something like this. Okay? So this is in combination with microwave background. And you can see that the degeneracy is only in the direction you expect them to be. But what is the answer? Where is it centered? Is it centered on a negative number, a positive number? Fortunately, it turned out that it was brilliantly centered in a region of parameter space where we thought that it was acceptable given our previous measurement. So if you do a statistical analysis and you compare the measurement for B1608 in the first lens with the measure for RxJ1131, the blind lens, you see they are consistent within the uncertainties. So these two measurements, even though the second one is blind, they're consistent with each other within the uncertainties. You combine everything, and these are the numbers that you get. Of course, the numbers are not so important in my view. I don't care if the Hubble constant is 75. But what is important here is that the measurements agree within the uncertainties. So it means that you're getting a realistic estimate of the uncertainties. And the uncertainties are interesting. See, from two lenses, you already get 0.2 on W, and you already get, below 10% on Hubble constant. Okay, and so yeah.
So can you go back one second?
Yes.
For the contours of from these two lenses,
Yeah.
how come they are so different
What do you mean?
in terms of size?
Well, part is the precision, and part is the redshift. There are different redshifts, so they rotate. And also the measurements don't have the same precision. Some of them are better precision than others. Some, there's more uncertainty in the line of sight correction, more uncertainty in the time delay. So they're not identical, but they're comparable. They're similar in size. See, the blue and the gray are not too different. The gray is probably a little better. Anyway, so, and again, you can compare with other probes, and it works really well. Compare with probes at that time, so we were doing really well with just two lenses, and like 10 people working on this. It wasn't like a satellite or anything like this. So it was a very small operation. Yes?
Sorry, in the plot just before, it's the H naught that you determine through time delay, right?
Well, not only H naught, you have some information also on the other stuff.
Okay, so do you depend really on the WMAP parameters or?
So the H naught is mostly determined very robustly by the method itself. There's some degeneracy left with the other